Very good morning. We were started for defining new difference operator, finite difference operators. So among them, we have defined these two operators. Let me go back and let me revise. So we have defined finite difference operators. So among that, we have first defined shift operator, which is defined by e fx is equals to f of x plus h. So it clearly means that it gives you the function value at the next nodal point. Okay, and we have already pre-assumed that we are going to work with the equispaced data. Okay, means the x naught, then x1 is x naught plus h, and then x2 is the two step ahead, x naught plus 2h. The size, the length between any 2 point is remain same. So you take any here, so it is remains same. That is x naught plus 2h and x naught plus 3h are distance apart is h. Okay, so we are working with equispaced data. So first finite difference operator we have defined is the shift operator, which is defined as when you give the input as the function of x, it will give you the function value at the next point, which is situated at the distance h. Okay, so when you apply e again here, so you will get up, you just go follow the definition that will give you f of x plus 2h. So two step ahead. So 2 time e will give you 2 time means you can 2 time applying function this e will give you the function value at the two step ahead. Okay, right. So similarly, you can define that e if you apply k times, that is given by the, you can have this is the form. So here note that we are not only restricted this k with the integer. Okay, this k is maybe positive integer. Similarly, you can define for the negative integer and for any rational number. Okay, so examples are here. So if you talk about what is the e to the power half, means it is give you the function value at the x plus h by 2. When what do you mean by e to the power 3 by 2 means the function, this is operator, you can say. Okay, this operator, right? E to the power 3 by 2, if you apply on f of x, it will give you the function value at x plus 3h by 2. And if you go for e to the power minus half f of x, it will give you the value x minus h by 2 and so on. Okay, right. So this is what the first difference operator we defined in the previous lecture. Okay, so another operator which we have defined is forward difference operator. And see, these operators are which we are going to define, they are related to each other, and moreover they will give you an approximation for derivatives. Okay, so how much good approximation it will give, that will come a little later. Okay, so forward difference operator is we are going to use the notation as you have this delta. Okay, so which is defined as delta f of x as the, so as the name suggests you, forward difference operator. Okay, so name suggests you that it's a forward, so it's going forward and means like forward means next nodal point, f of x plus h minus f of x. Okay, so that will give you the definition of forward difference operator, and you can actually prove that this operator is a linear operator. Okay, so that the definition of linear operator is okay, so when you will say if operator is linear, when it is linear with respect to scalar multiplication and addition of two vectors, you can say, right? So you have the, for if you are able to show this here, okay, if you are able to show for the given operator the following definition, that will prove that you this operator is a linear operator, like derivative. So derivative of sum of two function is, you can take that individual derivative sum. Similarly, if you multiply scalar, then you can take scalar out and function derivative and so on. So with that here, so with this property, if you apply again delta on here, okay, again forward difference operator, that will lead to, means like you are going to use the linear property here, then you apply on the first function minus apply on the second function, and then use the definition. So if you use the definition, so first difference operator becomes f of x plus 2h minus f of x plus h. The future value minus function value, minus the present value, you can say. Okay, minus this delta fx is by definition f of x plus h minus f of x. And if you open it up, it is the simplified form is here. Okay, right. Now we are going to move further, and we are going to again define delta. Once more, means we are going to apply delta one more time here, and then we will try to identify the pattern so that we could able to write the delta to the power k. Okay, right. If you look at here, so delta square f of x is as recalled you previously, that's a simplified form. So we are going to come out this 2c0, 2c1, 2c2. These are the binomial coefficients if you look at here. So we are going to relate with the power. Okay, so this power, or you can say how many times it is applied. Okay, so how many times integer order time only we are going here right now. So you are this see first coefficient is, you can recall this 2c0, this is minus 2c, this is 2c1, 2c2. We are not talking about right now positive or second. So yes, one more pattern you can observe here is positive, negative, positive, means alternatively the sign occurs. The third thing is f of x plus 2h, x plus 2, first point is at x plus function value at x plus 2s, second is at x plus x, third is at x. Okay, right. So keep these things in your mind. Then if you apply again the forward difference operator here on f of x, means 3 times you are applying. So you are, see, since this delta operator is a linear, so you are going to apply directly here and use the linear property. Okay, and if you open it up, so this is the simplified form. Okay, so that we have discussed at the last in the last lecture itself. So if you look at the again the coefficients of the first term, second term, third term, and fourth term, they can be given by the binomial coefficients, like 3 here, so power is 3. So if you relate here, so in this 3c0, 3c1, 3c2, 3c3. Not only that, you can again look at the pattern of positive, negative, positive, negative. Okay, so odd, so 3 is odd, right? So you are ending with the negative sign, right? Last sign is negative. If 2 is even, so you are ending with the positive sign. Okay, so these coefficients are of binomial, okay, and they are occurring in alternative sign, okay, and you are ending with the positive or negative, depends on the odd or even time you are applying. Okay, other thing is you are starting with x plus 3h, you are starting with x plus 3h, means 3 is what, 3 is how many times you have applied, x plus 3h, x plus 2h, x plus h, h. So function values are evaluated in this way. Okay, so if I wish to generalize this now, so I can write here, so from here what I can get is, so from here this if I follow this pattern, so what it will give me is delta k f of x is equals to kc0 f of x plus kh minus alternative plus minus, right, minus kc1 f of x plus k minus 1h plus and so on, plus or minus here, right, plus minus k c k f of x. So this plus or minus will depend. So if k is odd, it will be minus. If k is even, it is plus, right? Okay, so we are going to again we have a little later we are going to uh, find an alternative way to get this expression as well. Okay, so okay, so with this forward difference operator, so let's see how they will look like in that difference table. Okay, so you have the pair of data, so you have the pair of data xi comma fi. Okay, so given xi comma fi you have. Okay, and let's take only four number of points, so 1 2 and 3, and let's see the how will you write the forward difference table for given data. Okay, so you have so I will first write. Okay, so this is your x, let's say this is f. So the points are x naught f naught, x1 f1, x2 f2, x3 f3. Now we wish to write first forward difference table. Okay, so first forward difference. First forward differences. So if you go and check, there is no role of these nodal points, right? If you so means if you first forward difference means you are going to use these points, these 2 points. So for these two, using these two, you are going to, and what is there is f1 minus f naught. Okay, and this if you say the definition is delta f1 or delta f0, delta f naught, right? What is f naught, f1, f2? If I want to say what is fn is or fk is f of x, f of xk means f value at xk. So if you look at this delta f naught means f of x naught. What is the forward difference is f of x1 minus f of x naught. And f of x1 is f1 and f of x naught is f naught. So this is the delta f naught, that is equals to f1 minus f naught. Okay. Similarly for the using these two, f2 minus f1. So this is delta f1. And the last is here is delta f2, that is given by f3 minus f2. So these are the first forward differences for the given table. So you can again apply, right? And we can go for second forward difference column. So you are going to use this. Okay, so delta f1 minus delta f naught. Okay, so difference of this delta f1 minus delta f naught. And if you are going, this is if you simplify, what it is if you replace it f2 minus f1 minus f1 minus f naught, that is equals to 2 minus f1 minus f1, that is minus 2 f1 plus f naught. And if you recall, this is nothing but del square f naught. Okay, so second forward difference here. So if you go with this delta f1 minus delta f naught, that is nothing but delta square f naught. That's what just now we have verified. Okay, so second difference is given by delta square f naught, that is given by delta f1 minus delta f naught. Similarly here. Okay, so you are going to have the second forward difference here. So that using these two is delta f2 minus delta f1. That is going to be, you can verify that delta square f1, and that is delta f2 minus delta f1. So do you have any doubt here? So I'm going to rub it. I'm going to rub this. Okay. If you have doubt, you can ask. So I think this is a simplification only. And if you go back and check this, see f of x plus 2h minus 2 times f of x plus h minus f of x. So x is x naught. So it's a delta square f naught. So it's very clear here. So let me this because I just wish to make it Clear? Okay, right. So delta square f naught was delta f1 minus delta f naught. So again, forward difference, you are going to use these two. Okay, that is going to be delta square f1 minus delta square, sorry, no, I use reverse delta. So delta square f1 minus delta square f naught. Okay, so if you simplify this, okay, that will give you delta cube f naught if you simplify. Okay, right. So you look at here. So f. So if you look this table carefully, okay, if you look this table carefully, so function value at x naught, first forward difference at f of x naught, second forward difference at x naught, and third forward difference f at x naught. They are sitting in the downward direction. Not only if you're starting with f naught, if you're starting with f1, if you're starting with f1, they are also sitting in the downward direction, delta square f1 till delta square f1 is possible. For f2 as well. Okay, for f2, then delta f2, they are looking at the downward direction. Right? So when you are going to identify the forward differences of a certain of a function at certain point, you are going to make the forward difference table, and you are going to look in the downward direction, okay, in the this way. Okay, right. Okay. So let's move further. So we are going to define now one more difference operator, which is known as backward difference operator. Backward difference operator. So which we are going to denote by up means reverse delta. Okay, right. So now how it is defined is, so backward means like, so it's rather going forward, it's going backward. So it's from the name itself, should be clear that this backward difference of f of x is present value minus previous value. So in the forward difference operator, we were having the future value minus present value. So here is present value minus previous value. Again, you can verify that this operator is a linear operator. Okay, and if you apply this one more time delta, which we are going to denote it by delta square f of x. Okay, and then use the linearity of f of x minus f of x minus h, and if you apply f of x minus delta f of x minus h, use the definition. So this is equals to f of x minus f of x minus h minus f of x minus h minus f of x minus 2h. The present value minus the previous value. And if you operate up, that is equals to f of x minus 2 times f of x minus h plus f of x minus 2h. So look at the pattern here. Okay, again, so delta square f of x. So again, if you look at the coefficients, so keep in mind that this is 2c0, this is 2c1, this is 2c2. And again, alternative positive sign, plus and minus. Okay, one more thing is, earlier in the forward difference operator, you are starting with in the delta square f of x plus 2x, the second two step ahead. You are starting with here present only. Okay, so you are starting with present, then you are going two step backward. So f of x minus h, f of x minus 2h. Okay, right. So similarly, if you again apply delta, okay, so similarly that you can verify that delta q f of x will be, if you apply separately, okay, apply using the linear property here, and if you arrange all the things, okay, in right shape, so that will be f of x minus 3 times f of x minus h plus 3 times f of x minus 2h minus f of x minus 3h. Means you are starting with the present value and you are ending with the 3 step ahead in the previous back side. Okay, and you are having the coefficients as 3c0, 3c1, 3c2, and this is 3c3, right? So you can generalize this. So you have generalized one is delta kfx. So kc0, you are starting with the present only f of x minus kc1 f of x minus h plus kc2 f of x minus 2h and so on, plus and minus, alternative plus minus sign. Okay, so this is minus, alternative plus minus sign. So ending with plus or minus k k f of x minus kh. So again, you have the odd number here, odd backward difference, you have ending with minus sign. If we are having even delta scale, you are ending with the positive sign. If you are having again odd here, delta 1, you are ending with a negative sign. Okay, so odd and even. Okay, right. So let's write the backward difference table now for the same number of points. So given point is, you have been given with xi comma fi. I is equals to 0, 1, 2, 3. So again, fi means f value at the nodal point xi. And these xi's are, xi is equals to x naught plus ih. Okay, we are having equispaced data only. Okay, right. So you have here x, f. So you have x naught, x1, x2, x3, f value at x naught, f value at x1, f value at x2, f value at x. Okay, so first backward difference. So likewise earlier, so backward difference is, so backward difference of f naught is not possible because backward difference of f naught is f naught minus previous value, but previous value is not given. Okay, f minus 1 is not given. The previous nodal point at the function value at the previous nodal point does not know. Okay, so it's only possible you're going to have, this is f1 minus f naught. That's going to be again f1 minus f naught. So which you have the notation as delta f1. Similarly, using these two, you are going to have delta f2 that is equals to f2 minus f1. And if you going with this, delta F3 is equals to F3 minus F2. Starting with the present value minus the one step ahead, with back one step back. And if you recall, okay, from the forward difference table, so this is nothing but the forward difference of F naught. The second one is forward difference of F1, and this is forward difference of F2. Right? Means you're doing the same thing, the only the notations are changing. Okay? Right. So one table you are going to construct, and that you can treat as either with the forward difference table or backward difference table. Only one table needs to be constructed. So first column is clear. For second column, so second backward difference is going to be is equals to delta F2 minus delta F1. Right? Because you are going to use these two. So this minus this is only possible because you don't know the previous here. So delta F1 minus, so that's it. So delta F2 is the present and delta F1 is the previous. So that is going to be, if you simplify this again, F2 minus F1 minus this is going to be delta square F2. And which you have seen in the forward difference table. If you this is going to be is F2 minus 2F1 minus F0. So that is same as forward difference 2 times forward difference of F0, F at X0. Okay, right. Similarly for this case. Okay, so you have here delta square F3, that is equals to delta F3 minus delta F2. And if you go and check, this is going to be delta square F1. Now, third backward difference. So third backward difference is going to be delta square F3 minus delta square F2. And that is delta cube F3. That is equals to delta square F3 minus delta square F2. Okay, right. So if you compare carefully, so I'm just running this, okay. Delta square F naught. Okay. Okay, so you can look at the differences here. So whatever the simplified expression you are getting, they are the same when you are talking about backward difference or forward difference. Only the notations are changing. Okay, now note that if you are looking at the backward differences, so if you're starting with F naught, there is no other backward difference for F naught, right? Only forward difference of are exists. So if you are going with F1, so there is a one backward difference exists, that is the F1, and that is going in the upward direction. Now you are going to talk about F2. If you are going to talk about F2, then you have the backward difference at F2, then second backward difference of F2. There is no third backward difference of F2. So they are, again, this is an upward direction. If you are starting with F3, so you have the backward difference, first backward difference, second backward difference, and third backward difference. They all are in the upward direction. So when you are looking at the forward difference table or backward difference table, they are essentially the same. Only you should know how to use them or how to extract the backward differences. If you are looking in the downward direction and starting with f naught, they are the all possible forward differences. If you are starting with f3 and looking at the upward direction, they are all the possible backward differences f at x. Okay, so both the difference table remain same. Only the notation and the only the how to extract the backward difference or forward difference from them is only the important thing. Okay, right. So any doubts so far? Okay, so if it is no, let's go further. So now let's see what are the relationship between shift operator, forward difference, and backward difference operator. Okay, so we are going to look at the relationships now. Relationships between shift operator, forward difference, and backward difference. Okay, so that we are going to look at now. So we are going to only follow the definition. Okay, we are going to follow the definition now. Okay, so if you look at the definition of forward difference, let's say, so what is the forward difference of f of x? Is future value minus the present value. Right? Now, what is f of x plus h? Is the first shifting of f of x minus f of x. So what it is this is equals to e minus 1 f of x. So this one is usually denoted as the identity function. Okay, so this one is many times usually denoted as identity function in identity operator or identity function in mathematics. Okay, and so from here, so this will give you delta is essentially identically equals to e minus 1. So this implies delta to the power k is means you are going to apply e minus 1 k time, and if you are opening their opening in binomial coefficient with the okay, I open this, and what you will get is e to the power k, right? E to the power k minus kc1 e to the power k minus 1 plus kc2 e to the power k minus 2 and so on. So alternative plus minus will be there, and you are ending with the 1, right? So this is why, so if you apply e power k into f of x is f of x plus kh, e power k minus 1 f of x is f of x plus minus 1h, and so on. Okay, right. Similarly, okay, similarly, you can define the relationship between backward difference operator and the shifting operator. So yes, of course, from here you can also, so if I used to note that this also implies E is equals identity equals to 1 plus delta. Okay, so that's also this, you can give E in terms of delta and delta in terms of E. Okay, so both ways possible. So similarly, you are, so if you go follow the definition, the backward difference of f of x is f of x minus f of x minus h. And if you use the shift notation, f of x minus e to the power minus 1 f of x. And this is equals to 1 minus e inverse applied on f of x. So this gives you the backward difference is equals to, identically, is 1 minus E inverse. So this will give you, this implies E inverse is equals to 1 minus backward difference, or this is again give you E equals to 1 minus delta inverse S, right? Okay, then similarly you can go for now its power. Okay, so this certainly implies if you apply backward difference k time, means you are essentially applying 1 minus E inverse k time. So again use the binomial expansion. So what you will get is the formula what you have got in there. Okay, right. Okay, right. So this is if you f of x is can be identified by this. Okay, so this you can again open 1 minus x to the power k, and you know, okay, how to expand this when k is an integer. Okay, so that you can verify that this will be remain the same as what you have obtained earlier. Okay. Now, next we are going to we are going to define a new difference operator known as central difference operator. So we are going to define. So you so third we have already defined three operators. So one more operator we are going to define, which is known as central difference operator. So these all work we are doing to approximate derivative, okay, so that we can actually bound the error or actually get the desired accuracy. Okay, so those things we have in our mind. So center difference operator, which we are going to denote by delta. So central difference operator, so if let me first define how it is defined is delta f of x is defined as f of x plus h by 2 minus f of x minus h by 2. And we are also saying that this is a symmetric operator. Okay, because so it is using, okay, so this x is here. So you have x minus h by 2, and this is your x plus h by 2. So it is not using the current nodal point, it is using the points which are sitting symmetrically, okay, at equidistant from means one means one step ahead and one step back. Okay, not the one step, it's half step ahead and half step back, half step back, exactly. Okay, now how it will be useful is when you are going to use delta square. So see, when you're talking about the node points, so first central difference of operator means like delta f of x naught. Okay, so if I let me have this, so delta f at x naught, what it will give you is f of x naught plus h by 2 minus f of x naught minus h by 2. So none of the value on the right side is at any of the nodal point. Okay, because x1 is x naught plus h. Okay, and if you go back type x naught, that is going to be x naught minus h. Okay, the other nodal point, if you know by any chance. So on the right side, none of the function value at its nodal point, if you are going with first central difference operator. So that, so one more thing is again these all are difference operator are linear that you can. Okay, now one when you are going to apply again, so delta square f of x. Means one more time if you apply, that is going to be delta f of x plus h by 2 minus delta f of x minus h by 2. And if you apply the definition, so this is equals to f of x plus h by 2 is f of x plus h by 2 plus h by 2, that is x plus h, minus f of x plus h by 2 minus h by 2, that is x. That's for first term. For second term, you have f of x minus h by 2 plus h by 2. So f of x minus f of x minus h by 2 minus h by 2, that is minus f of x minus h. And if you simplify it, so if you simplify it, this will give you delta square f of x is equals to f of x plus h, f of x plus h minus f of x minus f of x 2 times f of x. So minus 2 times f of x plus f of x minus h. So second order difference, central difference operator using all the points, okay, x, x minus h and x plus h, means they are symmetrically seated. Okay, right. So okay, so why we have identified a new difference operator is because that this gives you better approximation for derivatives than forward difference and backward difference operator. Okay, means error in this case will be smaller than the error what will be occurring when you are going to use the forward difference and backward difference operator. Okay, so let's write down the central difference table as well. Okay, for the given data. So if I going to write, so you have this is x f. So you have x naught f naught, x1 f1, x2 f2, x3 f3. So first center difference will be what? So f1 minus f naught, what it will be? Yeah, so you if you are going to look at back, okay, so if you instead of x naught, if you use x naught plus h by 2, means 1 by 2 ahead. So if I go with this delta f half, what is delta f half? Will be means f half means what? So you have so if I say f of fi is f of xi, okay, and xi is equals to x naught plus ih. So what is x half is, I'm talking about is x naught plus h by 2. And what is f half is f of x half. Okay, so what is there is if I apply the first difference operator, so that is what f of x plus h by 2 minus f of x minus h by 2. So if I say I want to evaluate first difference at x half, okay, x means x half means x naught, then x half, then x1. Okay, so this is what is x naught plus h means you are going to means in the center. Okay, so this is the center x half, x naught plus h by 2. That is going to be, yes, f of x naught plus h by 2. So f of x naught plus h by 2 plus h is f of x, right? X naught. So that is going to be f1 minus f naught. So, right, if you replace x by x naught plus h by 2, so what it will be? F of x naught plus h by 2 plus h by 2. So x naught plus h, that is x1. And x naught plus h by 2 will get cancelled. So f of x naught. So that is f1 minus f naught. So the next one is one step ahead. So delta f3 by 2, that is going to be f2 minus f1. Because we don't want to create a new table. We just want to see the first column and second column and third column, how they will be looks like in terms of central differences, forward differences, and backward differences. Okay, then the last one is here is delta f5 by 2, that you can verify that that's going to be f3 minus f2. Now the second central difference, okay, second central difference, if you are going to have is f2 minus f1 minus this one, right? Okay, so this is going to be is if you are going to find out delta square f1, and this if you are going to use these two, you are going to find delta square f3, f2, delta square f2. Okay, right. Right. Then you have the third for third central difference. Third central difference. If you are going to use these two, so again, so odd means you are going not going to function value at the nodal point. You are going to get at some. Okay, 3 by 2 here. Okay, so that you just verify these terms. Okay, that is easy to verify by following the definitions. Okay, that will be easy. Now it is a one line formula. Now what we are going to define as Newton's forward interpolation formula or backward interpolation formula. Okay, before that, what we are going to do now is we are going to identify the relations between divided differences and forward difference or backward difference of it. Okay, so that then it will be easy to write the Newton's forward interpolation and backward interpolation. Okay, right. So we have, so let's now we are going to define relationship, because we know the Newton's interpolating polynomial in terms of divided differences. So if we are going to have the relationship between divided differences and the forward difference and backward difference, then its only job is to replace them by the given relation, okay, by the established relation. So relationship between that forward difference, backward difference, and divided differences. So we have been given with equispaced data. So equispaced data is given to us, equispaced. Equispaced data is given means xi is equals to x naught plus ih. So where I is running from 0, 1, 2 and so on till n. Now recall the first forward difference. F of x naught comma x1, and if you write it, f of x1 minus f of x naught divided by x1 minus x naught. If you recall the definition, so if you look at the denominator, x1 minus x naught is 1, means x1 minus x naught is h, right? So 1 by h time f1 minus f0. So that is equals to power difference of f0 divided by h. If I wish to write in the forward difference, if I wish to write in the backward difference, that is equals to backward difference at f1 by h. Right? So this is first divided difference related with the first forward difference and backward differences. So similarly, if you are going to with f of x1 comma x2, that is going to be 1 by h time f2 minus f1. Okay, f of x2 minus f of x1 divided by x2 minus x1. So x2 minus x1 is, they are only h distance apart, right? So this is going to be, so f2 minus f1 is delta f1 by h, and in forward and backward difference it is delta f2 by h, and so on. Okay, so this is first column is identified now, but we only require these things. Okay, so f of x naught, x1, and so on. So you, if I wish to write xk minus 1 comma xk, that is going to be is f xk minus 1 by h in the forward difference, in the backward difference fk by h. Okay, and k is running from, k is equals to 1, 2, and so on, n. Yeah, k is running from 1 to n. So these are all the first column. Similarly, for the second column is second divided difference now. So now for the second divided difference, if you have, so now, so that is f of x0 comma x1 comma x2. That is equals to f of x1 comma x2 minus f of x0 comma x1 divided by x2 minus x0. So if you recall, what is x2 minus x0 is 1 by 2h. And we wish to first write in the forward difference operator only. Okay, so that is, this is what is f of x1 comma x2 minus f of x0 comma x1. So what is it is 1 by h time f2 minus f1 minus 1 by h time f1 minus f0. So if you further simplify, this is equals to 1 by 2 h squares, h is common coming out, and you have f2 minus 2 f1 minus f0. And that is nothing but the second forward difference of at f0 divided by 2h square. And if you recall the forward difference and backward difference table, that is nothing but second backward difference of f2 by 2h square. Right? Okay. Similarly, others. Okay. Similarly, you can generalize this in the following way. So you can write the generalized divided difference, nth order divided difference as equals to nth forward difference at f0, nth backward difference at n fn. Okay, that is equals to, that's divided by n factorial time s to the power n factorial time s to the power n. So once you know this, okay, so once you know the divided difference table or forward difference table or backward difference table, you can certainly now able to write the Newton's forward interpolation formula and backward interpolation formula. Okay, right. So let's write the interpolating polynomial. So now we are going to write interpolating polynomial using forward difference and backward difference. So if you are going to use the forward difference, it's known as Newton's forward interpolation formula. If you are going to use the backward difference operator, is going to be Newton's backward interpolation formula. So certainly we are going to use the relationship between divided differences and this backward and forward differences here. Okay, so this formula is known as, I just wish you recall here, they are known as Gregory Newton formulas. Or simply Newton's formula. Okay, or simply Newton's formula. Okay, so let's write the forward interpolation formula. So when you have the equispaced data, okay, then the things will be simplified. Okay, in the simplified form. Forward interpolation formula. So we know that so p of x, the interpolating polynomial, is equals to f of x naught plus x minus x naught into first divided difference x naught comma x1 plus x minus x naught into x minus x1 times second divided difference and so on plus x minus x naught and so on and so on times x minus xn minus 1 f of x naught x1 on xn. Now if you use the relationship now, okay, so this is equals to f of x naught is if I okay fine, f of x naught plus x minus x naught is as it is. So first forward difference at x naught x1 is delta f naught by time x minus x naught. Second forward difference was delta square f naught by 2 factorial time h square x minus x naught into x minus x1 and so on. The last term is nth forward difference at f naught divided by n factorial time s to the power n time x minus x naught and so on x minus xn minus. So note that, see, we have learned that the theorem, okay, that interpolating polynomials may have different representations, but they are unique. If it means the final expression, okay, if you are going to simplify everything, the finally polynomial what you are going to get, that is unique. Okay, so error will not be changing. Okay, error will remain same here. Okay, so error term will not be changing, error term will be remain same expression. So here we can identify the error now. Okay, so so error will be remain same. So error in interpolating, so error in interpolating polynomial okay, so which we are going to define as means f x is equals to If you recall, that is equals to x minus x naught to x minus xn divided by n plus 1 factorial time f n plus 1th derivative at some z, where z lies between x naught to xn. Right? So we have just now worked with the forward difference and backward difference operator. And when you wish to bound, so when you're going to have mod, so you're taking the mod in the both side, is for bound this is equals to, so 1 by n plus 1 factorial time mod of this, the polynomial of degree n. Okay, so we are going to make it less than equals to, we are going to take maximum over this product x minus x naught to x minus xn, where you have this x belongs to x naught to xn. Time, this is this time maximum of z belongs to x naught to xn, which we are going to define as mn plus 1, if you have recalled maximum values. So we have somehow we got the approximation we have got this because this is known to us. But in many situations, the function may or may not be known. So we wish to approximate this term, okay, so that we can check the error accuracy and so on. So that we are going to now, we are going to identify the relationship between forward difference and backward difference and derivatives. Okay, right. So so similarly, but just the forward interpolation formula just by replacing the first forward difference and first divided difference, second divided difference, and so on, and divided difference by the relationship between them with forward differences. So delta f naught, delta square f naught, then these all can be identified from the difference table. Okay, so similarly, you have also noticed what we have defined previously, relationship between the divided differences and the backward difference operator as well. Okay, so when you are going to look at the, okay, when you are going to see there, you are going to, again, you can identify the backward interpolation formula also there. Okay, right. Okay, and we are also going to identify an alternative way for getting this forward interpolation formula. And then with the following, say that then it will be very easy to memorize as well. Okay, right. We wish to approximate the derivatives now. Okay, so that we are going to do maybe in the next lecture. Okay, fine then. Okay, thank you.